Hi everybody! Today we are going to discuss the third part of acid-base titration, the effect of acidity on distribution of dissociated species of weak acid or base. In the equilibrium system, weak acid or base can't dissociate completely, so the solutes usually exist in more than one form. Based on the dissociation equilibrium equation, concentrations of different forms of solutes change as the acidity varies. In analytical chemistry, we can take advantage of this property to control the concentration of certain species by tuning the solution pH to make the reaction complete or shield some interferences. It is of great practical significance to discuss the effect of acidity on distribution of dissociated species of weak acid or base. From the dissociation equation of weak acid or base, we can see that when the conjugate acid-base pairs are in the equilibrium state, there are various forms of acid or base present in solution, the concentrations of which are called equilibrium concentration. The sum of concentrations of these acid or base components is referred to as a total concentration, commonly expressed with C. In equilibrium state, the proportion of the equilibrium concentration of one certain form in total concentration is called the distribution fraction, expressed by delta. According to the definition, the calculation formula can be written as: we'll start from the simple case, monoprotic weak acid, delta of monoprotic weak acid, HA. Assuming that there's only HA and water in solution, the dissociation equilibrium is HA turns to hydrogen and A. Total concentration of HA is expressed as a sum of equilibrium concentrations of dissociated and undissociated HA. So the distribution fraction of undissociated HA, delta, can be represented as follows. The undissociated HA is also involved in the dissociation constant expressed in this equation. We notice that there is a same factor in these two expressions, so the constant equation is substituted into distribution fraction to make some transformation. After arrangement, the distribution fraction can be expressed by Ka. The denominator here is hydrogen plus Ka, and the numerator is hydrogen. Pay a little attention to this form, and it will be used again later. Similarly, we can obtain the expression of distribution fraction of conjugated base, in which the denominator is also hydrogen plus Ka, and the numerator changes to Ka. It's obvious that the sum of these two fractions is 1. By comparing the two expressions, it can be seen that both denominators are the same, and the numerator is one term of denominators respectively. In the expression of conjugate acid, the numerator is hydrogen, while that of conjugate base is Ka. Plot delta HA and delta A separately as a function of pH to get the distribution diagram, in which red curve represents delta HA and black curve represents delta A. As shown in this figure, we can see that 1. As the increase of pH, the ratio of conjugate acid decreases while the ratio of base increases. Second, the two curves cross at pH equals pKa. Third, when pH is less than pKa, acid form HA is predominate. When pH is larger than pKa, A is predominate. Compared with the simple form of weak monoprotic acid, the distribution fraction of polyprotic acid is more complicated. Taking weak binary acid as an example, first write down the stepwise dissociation equation to get the corresponding dissociation constant, and then transform the expression with concentration of conjugate base. The total concentration of the weak binary acid C is expressed by the sum of concentrations of its three acid forms. Rearrange the formula by substituting the concentration expression of each conjugate base. According to the definition, the distribution fraction of undissociated acid equals the division of its concentration by total concentration. Final expression can be obtained after rearrangement. Also pay attention to this final form. In the same way, according to the definition, the distribution fraction of conjugate base HA and A produced after the primary and second ionization can be obtained by making some transformation to the equation. Comparing the three distribution fractions, we can find that their denominators are the same, and the numerator is one term of the denominators, which is characterized by the fact that the number of hydrogen ions in the term is the same as the power of the hydrogen ion concentration, and the reduced hydrogen ions are replaced by the corresponding dissociation constants. As an example, the plot of distribution fraction as a function of pH for acetic acid shows that the pH range of 6.1 to 10.2. There are three acid forms, due to the small difference between Ka1 and Ka2. Besides, we can also get the information that if pH less than pKa1, H2A is predominant. If pH is larger than pKa1, A is the predominant form. If pH larger than pKa1, A is the predominant form. If pKa is in between pKa1 and pKa2, HA is the predominant. For weak triprotic acid, the distribution fraction of each acid form can be deduced through the same process. Generally, there are N+1 forms for polyprotic acid with N hydrogen ion. So, 4 forms exist in the system of triprotic acid, and the distribution fraction of each form can be expressed in this way. The numerator of first form is the first term in denominator, and the second form corresponds to the second term. The third and fourth forms can be deduced follow the same rule, making the diagram of distribution fraction versus pH. We can get the distribution plot of 4 forms for phosphoric acid. Summary: there are N+1 forms in solution of polyprotic acid with N hydrogen ions. Properties: distribution fractions of all these forms have the same denominator, composed of N+1 terms and arranged in the descending order of the power of hydrogen ion. If the power reduces by 1, the relevant dissociation constant will make up. The highest power of hydrogen concentration is N, which is consistent with the number of hydrogen ion containing in original acid molecule. Numerator: it is the same as one term in denominator, corresponding to the dissociation condition of the specific form. That's all for today. Thank you. See you next time.